Good morning, everyone. How's it going today?
Hi, Professor. Good, and you?
Good. Thank you. Morning. Okay, so just some quick announcements regarding the midterm. The average is 68%. That's quite good. When we were doing these type of exams in person, this is even usually on the higher side for the first midterm. Usually we will improve a lot by the second midterm. So 68% is pretty good. You should already see your score, and a few of you have contacted me regarding wanting to be able to earn some partial credit. So I'm offering an opportunity to possibly get some partial credit, and let me show you what the policy is. Okay, so let me go to this tab. Now for our first midterm, there are 3 questions where you have to calculate an answer and enter your numerical answer. These are questions 17, 18, and 20. Now, if you did the calculation wrong, if you get a number wrong, you do not receive credit on these questions. But if you get it correct, there's no need for you to make up for any extra partial credit. But if you did get any of those questions wrong, or 1 or 2 or 3 of these wrong, and you believe that your work, there are some good correct element in your process, and we do value the procedure, we do value the process. Now you can take that work and resubmit it under the exam 1 partial credit tab, which is right below exam 1 under week 7 folder. Okay, so do not include any multiple choice. Also, I'm going to look at which one you got wrong. If you got it correct, I will not look at, even if you submit, right, there's not going to be any extra points, of course. So what kind of work should you submit? I'm not really asking you to, check a solution somewhere or rewrite it. Basically, whatever your thought process was on the exam. And if you wish to share that with me, you can take a picture of your work out, or if you don't have it with you, you can replicate it and submit it. So for example, if your answer was 30 newtons, now what you submit now should reflect that. I will grade this based on what you did in the exam, and also now your process, to possibly give some partial credit. But I have to look at the process. Okay, so if there's process I still believe if there's nothing can be awarded, then maybe no points will be, extra points will be added. But if I see good elements there, then I will add partial credit onto your exam score. So this assignment is not scored. Okay, so whatever I look at here, I will go back and change the exam score if it's warranted. Are there any questions about this particular opportunity for partial credit?
Is there a limit on how many we can submit?
Yes, 3, questions 17, 18, and 20, because these are, if we were to do this in person class, these would be what you write down on the paper and hand it to me. So this is essentially try to be similar to that. You can show your process by writing these on paper and then submit it.
Okay.
Any other questions?
So just to, sorry, go ahead.
No, you can go ahead.
All right, so just to confirm, so we're showing the process of our incorrect answer, right? We're not actually correcting it.
That's correct. You're showing your process of the incorrect answer because we wanted to justify sometimes even if our answer is wrong, they're part of our process that's still correct. And I want to be able to acknowledge that.
All right, thank you.
Okay, yes, the question I had was, I think it was for number 19. I drew the force diagram wrong. And then based on that incorrect force diagram, I did my calculation for number 20.
Yeah.
So would that be like count for like partial credit? Like even though it was using the wrong force diagram, if my calculation was correct to the force diagram that I did draw?
Yes, yes. So
Okay.
if your force diagram has your friction in the reverse directions and everything else is the same, then if everything else is correct, but you get a wrong answer because you had flipped the direction of your friction. Now, even if I were grading this on paper in person, it wouldn't be 5 out of 5 for question 20. So if everything else is correct, just the final number is wrong, maybe I'll put 4 out of 5 for that question.
Okay, thank you.
Sure. Any other questions?
Is this like the only opportunity we have to make up our grade for this particular test? We'll like to improve on it.
Yes, I usually do not curve the exam because if you curve it, I don't think there's any meaning to it, right? If everybody get a higher score or low score, if you always curve it, then there's no point in learning. But this is an opportunity for you to to get the credit that you deserve, that you showed you're learning some correct element in your process. I usually do not curve individual exams, but at the end of the semester, when I have all the grades compiled, have the final grades, I usually will curve on that. It's really no difference than, not too much of a difference than, curving every individual exam rather than curving the final grades. So that will be another opportunity. Now, if I do curve it, it will not be harsher than the ones that's being established in the syllabus. So the syllabus as of right now, if it says 90 above is A minus and A, so if there is a curving occur, it would not be in any direction that make it harder. It will always make it in the direction that student grades improve. So that's possibly will happen. Also, you will have the extra credit of doing the post-assessment, just like how you did the pre-assessment. That's 1 extra point on the final grades.
Okay, and for that post-assessment, will it be graded on correctness for this time?
No, it will only be graded on honest participation.
Okay, thank you.
See the score in Canvas because I still need to know what the score is, but I'm not going to count that score in your grades. It will be converted to an extra credit at the end.
Okay, so even if we did really, really bad on the pre-assessment, because I personally did really bad on it, will we still get some extra credit for that?
Right, as long as you look through the question without randomly clicking A, B, C, D, as long as you actually look through, then you get the full extra credit.
Okay, thank you.
Yeah. Any other questions?
Will you be changing our grades for the pre-assessment anytime soon, just because we don't know our real grades?
Yes, usually after the second midterm, before the final, I will give everyone a grade, a calculation, what their current grade is and the projection of their final grade in the course.
Okay.
Any other questions? Okay, so if you do think of any questions later, feel free to email me. Today, we will continue to talk about how to calculate work. Why do we care? Because work is ways to change energies of a system, right? You can do work on the system and that will increase as an energy input into the system or decrease the energy of the system that will become an energy output. So their work is done by all different kind of forces because what is the definition of work? Is you apply a force over a certain displacement, right? So work is done by the various forces. And these are all the forces we have looked at in this semester. So do we know how to calculate the work done by these individual forces? So now let's look at some concrete examples going through the list of the work done by these forces. First, let's look at gravity. Okay. Here I'm using 2 different ramps. They are of different height. They're of the same height, but different lengths. They have a different angle. What is the process of work done by gravity on the block in the 2 situations? Are they the same or are they different? So to calculate something, always recall the definition. So when it's asking about the work, think about what is the definition of work? And you realize, oh, it says work is a force dot into displacement. Now, if it's a constant force, you don't have to use the integration formula because it's a constant. You can just use F dot into dr. So let's look at these two vectors for gravity. In which direction is gravity? Gravity is always pointing straight down, right? So this is gravity, Fg, which is equal to mg. And during this process, let's look at the first ramp. From the top of the ramp to the bottom of the ramp, what is the displacement vector? How do I draw delta R? How should I draw delta R?
Y final minus Y initial.
In terms of what it matters for the work done by gravity, you're right. It turned out eventually we realized only the Y, the vertical direction matters. At this point, we don't know that yet. We're simply saying, okay, displacement is a vector pointing from your initial point to your final point. So if the block originally is here and eventually is here, then displacement is simply pointing from where it was to where it is later. So displacement will be along the ramp downward. Do you agree?
Yeah, I see.
Okay, so now it's asking us to calculate Fg dot into this delta R that I draw according to the graph I draw. How do I calculate this dot product? Well, okay, so dot product using the math knowledge, we know is the magnitude of the first force, which is mg, right, times the magnitude of the displacement. So what is the magnitude of displacement? It's basically from the beginning of the top of the ramp to the bottom of the ramp. So it's the entire length of the ramp. So it's the entire length of the L, right? I don't know what that is, but I can put L there for now. Dot product also says it's A times B times cosine the angle between these two vectors. What is the angle? The angle is between G, FMG, and L. And you can see it's this angle. This angle is labeled, is this angle labeled on my graph? I have two angles given. One is phi, one is theta. The angle I need, the angle between gravity and displacement, is that angle given? Is it phi? Is it theta?
Is it phi?
It is phi. You don't be fooled by drawing these lines one more time, but you can see gravity is really just this line. It's parallel to the vertical line. And this displacement, we said, is really just along the ramp. So it's parallel to this ramp. You can see this angle, even though I draw it here, is really just phi. Okay, so it's mg L cosine phi. And what is L cosine phi? Look at this right triangle using trig. Can you tell what L cosine phi is? Cosine phi is H over L. So L cosine phi is what? Is it clear from the diagram that L cosine phi is simply H?
Yes, so would it just be cosine phi times L?
Yeah, cosine phi times L is H, the height of the ramp. Very good. So what do we have derived? We have derived the work done by gravity for the first ramp is mgh. Okay, it has nothing to do with the angle. Angle theta never enter into the picture. Yes, you have a different angle theta, which means you have a different phi in these two different diagrams, but also means that you have a different length of L. So it turned out L cosine phi always give you H. So you can do the calculation one more time for case 2, but you know that you will get the same answer, mgh. And what does that tell us? That the work done by gravity only depend on the mass of the object and the height, the vertical height. So the angle actually doesn't matter. Okay, mg.
Professor,
Yeah.
maybe consider doing this example, but like calculating the dot product from the component forces, because I think maybe that way would be more intuitive in this case.
So you want to look at the component of gravity that's perpendicular to the displacement?
So what we could like maybe try is doing the horizontal component and the vertical component of each with that definition of the dot product, because I think maybe that makes more sense.
That's totally okay. That is another way to do this dot product. You can interpret it differently. So for example, if you wanted to say, okay, well, this is my displacement. Gravity has a y component and an x component. The y component doesn't do any work along this displacement. Only the x component is doing work. So what I'm using is f of x times L. I don't know which one should be simpler. Okay, but we'll see. If you were to use that, f of x is mg sine theta times L. Okay, and then you group L and sine theta together, you get h. So the same result. It's just a different interpretation of how you wanted to interpret this dot product. But eventually you get mgh, which is only depend on vertical height. And does mgh ring any bell for you guys? Have you ever seen this combination appeared previously?
Potential energy.
This is also equal to the potential energy, gravitational potential energy. Is this a coincidence that the work done by gravity is the same number as the potential energy?
Probably not a coincidence.
It's not a coincidence. Exactly. The reason for that is, well, whether you calculate work done by gravity or you look at the increase of gravitational potential energy, it depends on your point of view of the same physics process. If you had included Earth into your system, then the system has potential energy, gravitational potential energy. You're accounting for that using energy, potential energy. However, if you're calculating work done by gravity, even though you had not say it out loud, but implicitly, you are not looking at your system does not include Earth. So your system has block only, okay? So if now Earth is not part of your system, you can't really talk about gravitational potential energy anymore. You don't have it because Earth is not in your system. On the other hand, you will say, well, gravity is not in my system. Gravity is now an external force. It used to be internal, but now it's outside of your system. It's external force. So external force can do work, and it did work. It did a amount of work of mgh. So which means in the conservation of energy problem, you have a fully freedom to choose your system to include or exclude Earth. In the past, we had always included Earth because we wanted to use potential energy. But in the future, from now on, you can decide not to include Earth, but look at work done by gravity instead, and consider that to be part of your energy transfers. Okay, so in this case, the work done by gravity is positive, right? And the object go down, you probably think, well, it will speed up as it goes down. So this part of work done by gravity is considered an energy input into your system. So you account for the mgh in the input part of the equation. If you had include Earth in your system, you will account for mgh as a potential energy. and you do not consider work done by gravity, because gravity now is part of your system. Okay, so this is very subtle difference, but it's important to be clear and explicit what you mean by MGH. If you were not explicit, you might count MGH twice. You count for potential energy and you count for work done by gravity. Well, that will give you a wrong answer. Now, we will look at concrete examples later. But now, continue. Go ahead.
Sorry. So then, I'm kind of confused on why we wouldn't include Earth, because Earth has to do with gravity.
Your system, the choice of your system is completely up to you. So you can decide to say, I want a big system as much as big as possible. I want to look at the entire universe as my choice of system. That's okay. Or you want to say, oh, I only want to look at the solar system as my system, or I only want to look at Earth as my system. That's all totally up to you. It's your choice. Now, gravity is a force between the Earth and the block, right?
Right.
So if you had included Earth in your system, let's say I'm call this entire box my system, then this force is internal. It doesn't do work on your system. The internal force can't do work on itself. However, if you choose a different system, which means, oh, I'm only boxing up little m, so everything outside of it is not part of the system. So this gravity become an external force and now can do work. Does that make sense?
Yeah, it is.
So you only have two choices: include Earth or not to include Earth. We will talk more about this later. If you include Earth, you will talk about potential energy. If you don't include Earth, you will look at the work done by gravity, but you cannot do both. Either way, they will have an MGH term come out of your equation. So no matter which method you choose, you will get that MGH term, just with different it has different meanings depending on your choice of your system. It's a very subtle point. I'm glad you asked about it, but we'll get to practice a little more later. But first, let's continue to look at force done by other forces. So you can see for the gravitational force, the work done is independent of the path, because previously we had said, okay, you have a longer path or you can have a shorter path. The work is the same. It depends on the vertical height. It's not, so you can even have a zigzag path and the work would have been the same as well. So these type of forces, we call it conservative forces. Now this is just the label. But there are type of forces where work actually depend on the path. If you take a longer path versus a shorter path, the work is different. These are called non-conservative forces. As far as calculating conservation of energy, you don't really care. As long as you know how to calculate the work, you don't have to memorize which one is conservative, which one is not conservative. So frictional force is an example of non-conservative forces. Now, this is probably intuitive. Now, if you, from here to here, if you have take a longer path, well, you can see that you have probably a lot of more heat generated through friction. Or if you take a shortest path, go straight from this point to this point, then you probably have less heat generated from the work done by friction. So it actually make a difference. So let's take a look at a couple questions. So imagine if you push a 1 kilogram mass. Okay, this is your little object, and move this on the wall at the square loop, 1 meters per side. And the final position is 0.5 meter below the original position. So you start here, you end up here. Now, if we were to calculate the work done by gravity, what do we get? So think about the definition. The work done by gravity is what? Is the force of gravity dot into the displacement. Okay. I'll let you go ahead and vote here, but I can give you a hint. We have already talked about no matter what the process or the path is always MGH, right? But the MGH can be positive or negative, okay? So think about in this case, the number should be MGH, but would it be a positive MGH or negative MGH? Right, so go ahead, and then if you need a minute to think about it before you vote, feel free to take the time. All right, 10 more seconds. Let's go for 10 more seconds. Okay, all right, let's go ahead and end this. We'll take a look at our responses. All right, so majority agree on the magnitude. Choice B and D are all 5 joules. Very good. We got that from looking at MGH. M is 1 kilograms. Use G as 10 approximately. And the H is half a meter. Indeed, I would get 5 as a magnitude. So would that be positive or negative? So in this case, do you think gravity have done positive work or negative work? Anybody? And how do we figure it out? How do we figure out whether it's positive or negative? Is there some quick way to decide?
Because our final position ended up lower,
Okay.
I'd say that was like negative height. So with my H term being negative, I had a negative value times 2 positive values. So that's how I ended up picking -5 joules.
I see. So whether something is a negative value or not, because it's all relative, what you care is about the direction of your gravity and your direction of your displacement. So from your starting point to the finish point, even though you go through a zigzag path, the displacement is still simply pointing down. Okay, you call that delta H. Let's just call it delta R. Delta R is now I understand what you mean by putting a negative number on it. If you had the phi, you say, okay, I want up to be positive. Okay, then you will call it negative. I agree. However, in this case, gravity is also down. So gravity is 10 newtons, but also in the negative y hat direction. Okay, so they're both pointing down. So you can assign a negative sign to both of them, but when you do a dot product, you can see that goes away and become positive. Okay, you multiply these together, you get a positive 5 joules. So a really quick way to check whether gravity done positive or negative work is simply just look at the directions of the displacement. Gravity is always down no matter what, right? Then if you're going down also, then gravity does positive work. But if you're going up, when I mean going up, meaning your final position is above where you started, then gravity did negative work, okay? So only look at the direction of the displacement, whether it's also pointing down just by gravity, or is it opposite to gravity, then the dot product will become negative, right? So in this case, 5 joules positive. But now let's say, what if we're looking at, sorry, go ahead.
Oh, sorry. So I just wanted to clarify. So since displacement was going in the downward direction, and gravity and it's in gravity's like natural state to go downward, then that's why it's positive, because it's going in the direction it's supposed to go.
For
makes
the dot
sense.
product, for the dot product, if two vectors are in the same direction, then the dot product is positive because this is a times b times cosine theta. If they're in the same direction, this is 1, so positive, right? But if it's opposite direction, you can see that if one is a, one is if opposite direction, you get a 180 from cosine theta, and cosine 180 is -1, so that's negative, right?
Okay, I see. So since the displacement is and the force of gravity is going in the same direction, then that's why it's positive.
Yes, yes.
Okay. Thank you.
No problem. Okay, so let's look at friction. Friction does depend on the path. So if you were to look at the total work done by friction during this journey, what would you get? It does tell you the magnitude of friction is 2 newtons. Okay, so I'll give you, go ahead and then think about it for a minute and then put in your answer. So there, from the starting point to the finish point, the path does matter, but the friction keeps changing direction. So from here to here, to point A to point B, I'm going to label all these points, okay? A, B, C, D, and E. From A to B, I'm going up, friction points down. From B to C, I'm going to the left. Friction is again opposing where I was going. Friction is going to the right. And from C to D, I'm going down, friction will be going up. From D to E, I'm going right, and friction will be going to the left. Looks like friction always changes directions. So that means you cannot write one friction going through the entire thing. It makes more sense to break it down into different sections. So you can say, okay, the work done during from A to B, how much work is done? From B to C, how much work is done? From C to E, how much work is done? And eventually from D to E, how much work is done? And then you can add them up, okay? All right. 10 more seconds. Let's go for 10 more seconds. All right, any more votes? Okay, let's take a look at this together. We have a slightly more majority voting for D, C and D actually, and some for A and B. So it looks like we majority of you guys agreed on the magnitude, but again, the direction is different between C and D. We had separated this whole journey into 4 different sections, A to B, B to C, C to D, and D to E. What is one thing common about these different sections? That no matter, yes, your friction always changes directions, but if you look at the work done by friction at these 4 different sections, are they all of the same sign? Are they all negative? Or are they all positive? Or some of them are negative, some of them are positive? Can you, sorry, go ahead.
I'm not really sure, but would it have to do with like the direction of friction? Like it's going opposite of like the way the block is going or whatever it is?
Yeah, in fact, you can, without doing calculations, you can simply say, I know no matter which section you look at, you will always have friction in the opposite direction of your displacement. That is precisely correct. And very good. Thank you, Spencer. Also, Elaine said, frictional force is always negative in the sense that it's opposing the direction which way you're going. Yes, if you say, okay, I'm going to decide the direction of my displacement, which way I'm going to be the positive direction. So friction is always pointing in the negative direction. Then yeah, it's always negative. So what's important is kinetic friction is always opposing the direction of motion. So because of that, it's always in the opposite direction of your displacement. Displacement up, friction down. When you do a dot product between these, you get negative sign. Displacement to the left, friction to the right. When you do a dot product between these, you always get a negative sign. As I was trying to do it here, the first section is -1 joule, second section is -2 joules. And third section, again, -2 joules, because that's friction 2 times 1 meter, that's 2 joules, or 2 Newton meters. These two are, you can use both of these units. But again, it's again negative because friction is in the opposite direction. The same with the last section. So you add them all up, you get -7. So now after doing this process, you realize, oh, even though my friction is always changing directions, right? So this is not a constant per se. However, because even if it's changing direction, it's always opposing my displacement. So I could have just summed up all the displacement and multiply my friction. So even though FK 1 during section 1 is in a different direction than FK2 during section 2, than FK3 during section 3. But because they are always opposing my delta R, I could say the work done by friction is simply negative, it's always negative, magnitude of my friction times the total displacement, which is all of those added together, like 1 + 1 + 1 + 1 meters. So you get 3.5 meters and you get -7 joules. So you could actually sum them up, okay? Because it always gives you a negative sign. So for friction, yes, if you go straight down, you have friction, the work done by friction will be obviously 2 newtons times 0.5 meters will simply be 1 joule. But if you take a zigzag path, it will be 7 joules. So for friction, the work does depend on the path. So now we talk about 2. Gravity does not depend on the path. Friction does depend on the path. Any questions before I move on to talk about other forces?
I know you just said for kinetic friction, it always opposes direction of motion, but is it the same for static friction or is it only kinetic friction?
That's a perfect question because that's our next topic is, well, you have just showed us kinetic friction. What about static friction? That's a great question to think about. For example, this is a quote from a student who said, I don't think static friction can do work because it's static, right? That means there's no motion. The object is at rest. So if you don't have a displacement, how can you get work? Then work must be 0. Do you agree with the student?
I mean, maybe there could be a case where like there is some like gravity is going to do a work, or there you're on a plane or something, and that would be doing work, but you have another force, in this case static friction, opposing that work. So maybe that could count. Not quite sure though.
Yeah. So again, what the student said makes perfect sense. But when we go to evaluate work, we have to look at displacement. And whether something has displacement or not, something doesn't have a relative motion to the surface. The static friction simply, I have no relative motion to the surface I'm sitting on. Doesn't mean it has no overall displacement. So all you need to think of is to disprove what they said is, can you think of a counter argument? Can you think of a counter example? In fact, this is a question that we should probably have seen, is a counter example of that. Now, in this case, now we did look at this example from the force perspective when we do Newton's laws. When the object is moving together with the truck, the object has the same acceleration A. So which force is providing such an acceleration? It cannot be gravity. Gravity is downward. It cannot be normal force. So the only force that is providing such an acceleration is the static frictional force, which is pointing to the left. So do we all agree that static friction is pointing to the left and giving this acceleration to the block? That was from a previous question in dynamics, right? So does that friction do work? Well, it's pointing to the left, and well, has the block maybe making a displacement? Yeah, it's moving together with the truck from here, and then 3 seconds later, it will be at a different place. So it does have a displacement. So looks like static friction can do work. And if this is a counter example to the statement previously, is yes, you can do work. And in this case, the work is positive. Okay, the static friction is in the positive, in the same direction as your displacement, and the static friction have done positive work, And if you're using an energy conservation point of view, the box, the energy of the box, the kinetic energy of the box, do you think that energy is increasing or decreasing?
I think it's increasing as the truck is accelerating, meaning it's gaining more velocity.
Yes.
So therefore the boxes as well.
Yes, because velocity is increasing. So kinetic energy mv squared, 1/2 mv squared, also increasing. Well, where would that part of the energy come from? It has to come from somewhere. It has to come from your energy input. Now, in this case, you don't have an energy output. So this increased kinetic energy comes from your energy input. And that is the work done by friction. So this positive work done by friction goes to increase the kinetic energy of the box. So it makes sense physically. So kinetic friction always do negative work. Static friction, a lot of times static friction doesn't do work. He or she is right in a lot of cases, but sometimes it can do work, and we just found an example. So we have down 3 forces. Let's look at one more force. That's the work done by a spring force. Because spring will push an object, right? Will give an object the spring force, and there's work that can be done. So let's look at this. You have a block attached to a spring and it oscillates. We're looking at a process from 0 to x. So this is your initial point. This is your final point. To calculate work done by the spring, we use this very generic format. Okay, from 0 to x, from initial to final, we do force of spring dot into displacement. Why don't we say F of the spring times displacement? Why do we have to use integral here?
Oh, because the force can vary.
Force varies, very good. You can see from 0 to x, the spring force is bigger and bigger because you're stretching it further and further. So we cannot use this notation, that would be wrong. You have to use the integral. And the force does depend on where it is. And Hooke's law says this force is always opposing my displacement. So force of spring is x, k times x, okay? Negative k times x is always in the opposite direction, times dx, in this case, our displacement. So from where? From initial to the final. Okay, initial to the final. Initial is 0, final is x. So if you do this, you will calculate using integrals. You have got the work done by the spring force from 0 to x is negative 1/2 kx squared. Okay, it's negative because the direction of the spring is opposing the direction of your displacement. Okay, your displacement is to the right, but your spring is trying to pull it back to the left, so it's a negative direction. 1/2, but never mind the signs. But if you're looking at only the magnitude, 1/2 kx squared. Does that look familiar? Have you ever seen 1/2 kx squared elsewhere? Have you seen this somewhere else?
Oh, it's kind of like acceleration in our kinematics equations when we were doing like when we had x equals x naught plus v naught t plus 1/2 a t squared. It's just that now instead of an a, we have a constant k.
Yeah, you have a 1/2 kind of a square kind of thing. Yes, and Jacob also said, yeah, for kinetic energy, you have a 1/2 something like this. But those doesn't involve a spring constant. So didn't we talk about another type of a potential energy, which is the elastic potential energy, is the energy stored in the spring, which is 1/2 kx squared. So here is x because we are having a change in length from 0 point. So here delta x is x minus 0. Okay, so x is really just delta x. Now, if your initial point is x1, then you would have end up at x2. So your delta x will be x2 minus x1. So here we said x simply because we started at 0. Okay, you could have just said delta x to be more general. So again, here you see a very interesting case. is the work done by the spring have the same format as the energy stored in the spring. And that's not a coincidence. That's very similar to what we did previously. Work done by gravity is equal to the potential energy of the gravity object system. Again, this is a choice of your system, either to include spring in your system or to not include spring in your system. Depending on your choice, you will have this term to come up in different ways. They either come up as an energy term or they come up as a work done by your spring term. But either way, they have a 1/2 k delta x squared format. Okay, again, we will practice using that in real problems later, but now I just wanted to show how to calculate the work done by spring. All right, sorry, I'm out of time. I will see you guys next week. If you have any more questions regarding the makeup for your extra partial credit, please let me know. Otherwise, I will see you next week and have a good weekend, guys. Bye, everyone.
Professor, what I already emailed you, do you still want me to submit it to that assignment you created, or?
There is no need. If you already emailed me, then you don't have to.
Thank you.
Mhm.
Have a good day, Professor. See you later.
Okay. Thank you. You too.
Professor,
Yes.
I was wondering if you knew if there was any workshops for this class, like tutoring workshops. I know that they do that for chem, but I didn't know if they did that for physics as well.
Okay, let me search for that. I don't recall if I've seen this semester, but in the past, I do remember there are some learning resource center sometimes send out an email. Let me look for it, okay?
Okay, thank you.
Sure, of course.